Okay, lesson 3.6 today. We're going to talk about the different types of triangles. So we've done a lot with triangles so far here in chapter 3, but we've never really talked about the different kinds of triangles we have. So that's what we're going to learn today, and then we're going to also learn how to prove some different types of triangles. So use that idea in a proof. So here we go. Let's get started. The warm-up for today is just take a look at this triangle and just how would you describe it? I'm wondering how much vocabulary you have backed up from years past. So take a look at those numbers and think if there's more than one way that you could describe this triangle. Pause your video and write some thoughts down. All right, so when I look at this triangle, I see, well, I'm noticing that some of these numbers are the same. So I see that these two side lengths have the same length. So this would say that these two sides are congruent. Okay. I also notice that these two angles down here are congruent as well, right? They have the same measure. Oh, that's kind of interesting. The two sides and the two angles both have the same, have two congruent parts. But I noticed that the third side is 28 and the third angle is 46, so they are definitely different. So all three are not the same, only two. So if you remember, you could describe this as two sides congruent. You could describe it as two angles congruent. You could notice that, all three of these angles are less than 90 degrees. So you could say all angles are acute would be another way to describe it. So those are all some options. Now, each of those things actually has a name that we're going to remember. Maybe you already remembered the names of those triangles based off of two congruent sides or all angles acute. But that's what our lesson is all about today. So we'll get going on that. But I just wanted you to start being able to look at a picture, notice some numbers, and just start describing that triangle based on those different things. Okay, so there are different ways that we can classify triangles. We can classify triangles by sides, or we can classify triangles by angles. So we're going to start by classifying by sides. So if I look at, I have three different types of triangles. I have a scalene triangle, an isosceles triangle, and an equilateral triangle. And hopefully those are some familiar vocabulary words to you. So what I have for you in that first row, is I have a picture of each of those types of triangles already. So we'll notice in the scalene triangle, all three sides are marked differently. So for a scalene triangle, there are no congruent sides. All right. Now for an isosceles triangle, you will notice that two of the sides are marked congruent. An isosceles triangle is a really interesting, very common one that we use a lot. So you're going to see that there's some vocabulary words that are in there that we'll talk about in a second. But the main thing that we need to point out about an isosceles triangle is that it has two congruent sides, right? Two of those sides are congruent. And then if we look over at the equilateral triangle, an equilateral triangle, notice all three sides are marked congruent. So this is three congruent sides for equilateral. Now I often get the question of, well, is an equilateral triangle isosceles? And that, that kind of comes down to the definition of an isosceles triangle. It's not technically if it has two congruent sides, but if it has at least two congruent sides. We don't just always say the at least because it's kind of implied, right? Can you point to two sides that are congruent in the equilateral triangle? Yeah, I can. Those two are congruent, so it's isosceles. So technically, an equilateral triangle is an isosceles triangle because you have to have at least two congruent sides for isosceles. But we just usually only say two congruent sides because that's at the minimum, that's what it needs to have. Okay, so if we look at that isosceles triangle a little bit more closely, you'll notice some vocabulary here. So these segments that are marked congruent, the two sides that are congruent, we call legs. So that is some vocabulary that we're going to be using a lot. So when you know you have an isosceles triangle, the two congruent sides are called the legs. The third side then, the side that is not congruent, that is called, there we go, the base. Ooh, then you can't read it, sorry. So the side that's not congruent is called the base, and the two congruent sides are called the legs. All right. If we were talking about the angles in an isosceles triangle, the vertex angle is that side, or excuse me, is the angle that's between the two congruent sides. So the vertex angle is this angle between the two congruent sides. And then the base angles are the two that are down at the bottom attached to the base side. Hopefully that's pretty self-explanatory. But the vertex angle is definitely something that we talk about a lot when we're talking about isosceles triangles. So again, I'm hoping a lot of that vocabulary is familiar, but if not, make sure that you take note. Congruent sides are called legs. The angle in between the two congruent sides is called the vertex angle. The third side that is not congruent is called the base. All right, now I still have an empty box on each of these, and that is so that we can write down the good if-then form that we use for proving that a triangle is one of these types. So I'm sure that you can kind of identify these pretty well. That's probably something you've done before, but now we're going to actually write them in a proof, and so that's what we're going to practice, or what we're going to write down in this bottom box. So the idea that this triangle has no congruent sides, it's what's going to come into our if-then form for a scalene triangle. So if a triangle has no congruent sides, then it is scalene. So that's how you would use if-then form to convert what you know into, an if-then form to use in a proof. So if you're trying to prove a triangle is scalene, then you would say, if a triangle has no congruent sides, then it is scalene. Now, on the flip side of that, we also sometimes know it's scalene and want to then prove that it has no congruent sides. So the converse, since these are all definitions, the converse would be if a triangle is scalene, then it has no congruent sides. So you have both versions of the definition, the if-then form and then the converse. All right, so let's talk isosceles triangle now. This one gets a little bit trickier. So if I want to prove that it is isosceles, I have to know it has two congruent sides. So if a triangle has two congruent sides, whoops. Sorry, I'm trying to make it neat so you guys can read it. Okay, there we go. If a triangle has two congruent sides, then it is isosceles. So before I know it's isosceles, all I know is that it has two congruent sides. So that's how I'm going to write that. Now the converse on this one has a little twist to it. So this is why it's really important. I would put a star next to this guy coming up. So the converse is, if I already know it's isosceles, then I know that those two legs are congruent. So if a triangle is isosceles, then the legs are congruent. Now notice I changed the wording on that one, right? So in my converse, when I already knew it was an isosceles triangle, I know that I have two congruent sides, but I know exactly which ones they are. Whenever they tell us that we have an isosceles triangle, they will always tell us which side is the base. Triangle ABC is isosceles with base BC. So whenever they tell us we have an isosceles triangle, they tell us the base. So that means it's not just any two sides that are congruent. It has to be the legs that are congruent. So we really make sure that we are using that careful vocabulary when we're writing these if-then forms. If I don't know it's isosceles yet, if I'm proving that, then these two sides are just any two sides. It doesn't have to be any two specific sides, right? So if a triangle has two congruent sides, I don't know which ones they are yet, but if it does, then it's isosceles. But if I'm given that it's isosceles, then I know which side is the base, which means that the legs are the ones that are congruent. So be careful on your if-then forms there. All right, that's really the only tricky one, though. Then when we get back to our equilateral, that one gets a little bit more straightforward again. So if a triangle has three congruent sides, then it is equilateral And the converse of that, if I already know it's an equilateral triangle, if a triangle is equilateral, then it has 3 congruent sides. So you would use the converse if you knew it was equilateral and you're trying to prove the segments are congruent. You would use the original. If you have the triangle all marked up and you notice the 3 sides are congruent, then you could prove that it's equilateral. All right, so hopefully you have all of that written down in your notes. The original and the converse for each of those if-then forms, we're going to use all of those in proof. So have them down and get them ready. Okay, so that was classifying by sides. Now we have by angles, right? So we have an acute triangle, a right triangle, obtuse, and equiangular. So 4 different ways by angles. So if you notice that acute triangle, if you take a look at the measures of those angles in that picture, now be careful, it's not necessarily marked properly. Maybe we would want to do this, right? Because all 3 of those angles are different. They don't necessarily have to be for an acute triangle, but what they do have to have is 3 acute angles for it to be an acute triangle. All the angles have to be acute. All right. Now, the right triangle, you will notice that I have 1 right angle, and hopefully we're pretty comfortable and confident on how to mark a right angle, and that is to use that, to use that little box in the corner, right? Now you'll notice for a right triangle, can I have 3 right angles? No. Can you picture what that would look like? It would just be like an open box. It wouldn't be a triangle at all. Could I even have 2 right angles? Well, the angles in a triangle add up to 180 degrees. If I have 2 that are 90 degrees, what would be that 3rd angle? It wouldn't exist, right? So I can only have 1 right angle for me to have a right triangle. So a right triangle has 1 right angle. Now you'll notice in that right triangle picture we do have some vocabulary as well, and hopefully again that is some vocabulary that's very familiar to you. So we have one side that is the hypotenuse and we have 2 sides that are called the legs. So the hypotenuse is always the side that is across from the right angle. That's always the hypotenuse. And we also know that this will always be the longest side. I'll just write longest side. The hypotenuse is always the longest side. And then the other 2 sides we call the legs, similar to our isosceles triangle. So hopefully it'll be easy to remember. Okay, now we have our obtuse triangle. So if you notice in your obtuse triangle, how many obtuse angles do we have? Only 1, right? Only 1 obtuse angle in an obtuse triangle, and the same reason is for our right angle, right? I can't have 3. That would add up way more than 180. I can't even have 2. That would be more than 180 already. So I can only have 1 obtuse angle to make an obtuse triangle. So hopefully you're seeing there why you have to have all 3 acute angles for it to be an acute triangle, because if even just 1 angle is obtuse or right, then it makes it a different kind of triangle. So 1 obtuse angle for an obtuse triangle, 1 right angle for a right triangle, but 3 acute angles for an acute triangle. All right, and then our last one, hopefully, I'm sure you maybe haven't heard the word equiangular before. You've probably heard the word equilateral, but equilateral means the sides are all congruent. Equiangular means that the angles are all congruent. So an equiangular triangle is all 3 angles congruent. And since we know what the angles in a triangle always add up to, and if all 3 of them are the same measure, since they add up to 180 and they're all 3 the same, then each angle has to be 60 degrees. So we know that the angles are all 60 degrees in an equiangular triangle because they're all congruent. Okay, let's go back then and write our if-then forms. Again, these are pretty straightforward. The only tricky one that we had was the isosceles. So here, if we're trying to prove that we have an acute triangle, we say if a triangle has 3 acute angles, then it is an acute triangle. And the converse of that would be if a triangle is acute, then it has 3 acute angles. Depending on if you're given that it's an acute triangle or if you're trying to prove it's an acute triangle. All right, so then we have our right triangle, and this one is the one that we use the most often, I would say. So if a triangle has 1 right angle, then it is a right triangle. And then the converse of that, if a triangle is a right triangle, then it has 1 right angle. All right, now our obtuse triangle, the if-then form. If a triangle has 1 obtuse angle, then it is an obtuse triangle. Okay, and the converse of that one would be if a triangle is obtuse, then it has 1 obtuse angle. All right, and finally our equiangular triangle. If a triangle has 3 congruent angles, then the triangle is equiangular. Tough one to say. Kind of complicated to write too. All right, if a triangle has 3 congruent angles, then it is equiangular. All right, and then, let's see what color. Let's do this color. Okay, the converse then would be if a triangle is equiangular. Oh, can't fit it in. Sorry, we'll move it down to the next line. If a triangle is equiangular, then it has 3 congruent angles. All right, we've got all of our if-then forms there. Now, when we're talking about angles, we call the angles acute, but obviously on any of those, wherever you have that word acute, you could swap that word out for an angle less than 90 degrees, right? If you wanted to. Oops, I probably not here, but it would be this one down here when you're talking about the acute angles, right? You could swap that out for if a triangle has 3 angles less than 90 degrees, then it's acute, or if a triangle is acute, then it has 3 angles that are less than 90 degrees. So you could swap those out. Again, right angle you could swap out for 90 degrees. Obtuse angle you could swap out for angle greater than 90 degrees, greater than 90 degrees. And then the equiangular, I guess 3 congruent angles could be 3 60-degree angles, but you'll get congruent anyways. So just keep that in mind, that you can swap those words out if you want to. You can swap this out for a 90-degree angle here, right? Or you could swap out in this one, we could swap out an angle greater than 90 degrees if we wanted to. Okay. All right, so we've got all of our definitions, we've got all of our if-then forms. I'm sure if we gave you pictures, you'd be able to tell us which type of angle or triangle it is. So let's talk about how to do it in a proof, because this is really the only new thing to you for this lesson. All right, a lot going on in this picture for sure, and I'm seeing some overlapping triangles. I'm hoping you are as well. So first given is angle 1 is congruent to angle 3. 1 congruent to 3, okay? Second given, angle 2 is congruent to angle 4. 2 is congruent congruent to 4. Okay. Step 3, segment JP is congruent to segment PO. JP congruent to PO. All right, now I'm trying to prove triangle KPM is isosceles. Whoops. KPM is isosceles. Well, if I'm going to try and prove that that triangle is isosceles, I'm going to have to prove 2 of the sides are congruent, right? Now, just looking at the picture, I'm guessing we're going to try and end up proving that KP is congruent to PM. That's probably my goal for this proof, right? Okay, now I'm going to try and prove that those 2 sides are congruent. I do see some triangles jumping out at me that would help us, that would have those sides, right? If I could prove that this triangle was congruent to this triangle, then, you know, those would be CPCTC, and I could do that. I see that I have a side up here and an angle. I see that I have, you know, this side up here and an angle. But I don't know how I would get anything else. So while those 2 triangles would be really easy, I don't think I have enough information to prove that those triangles are congruent. So what other triangles do I have? Well, if I don't do those, I'm hoping now, after you've done some work on yesterday's lesson, I'm hoping you're going to see these triangles start to jump out at you. There's one there, triangle JKM. And then here's this triangle, triangle OMK. And I notice that I have down here at the bottom this reflexive, right? Okay, now if it's easier, if you need to, you know, again, draw those triangles up above if you have to, help you see it a little bit. OMK, right? And then triangle. Oops, here's M, here's K, and here's J, right? Now, we just noticed that this is a shared side. That's reflexive property. Oops. So I definitely want to indicate that in my picture. What else do I have? Well, I do know that this angle 4, this bottom right corner in my pink triangle, is congruent to angle 2, this bottom left corner in my green triangle. And I did say that I have this reflexive property down here, right? Let's go ahead and get that into our proof. Segment KM is congruent to segment KM, and that is the reflexive property. All right. So now, again, it is a little bit easier to see it when I draw it separately up top. So I'm looking at those 2 pictures up top. I'm trying to figure out, what do I need to prove these congruent? So I could have, if I could get this side over here, right, would be congruent to this side over here, then I would have side angle side. But those are the long sides. I don't know that the long sides are congruent. All I have is JP and PO. That's just to the top 2 little parts, right? So I don't have that. What about this angle 1 and 3? Oh, hang on. What if I combine over on the left? What if I combine angle 1 and angle 2? What if I do a little addition property? So if I combine these guys like this, and then I combine 3 and 4 on the other side like that, that would give me this big angle by angle M over here, right? OMK would be congruent to this big angle by angle K over here, JKM. Those 2 angles congruent, and then I would have angle side angle. Okay, so I need to combine angle 1 and 2, combine 3 and 4, and that's the addition property. So my step number 5 will say angle JKM is congruent to angle OMK. And we're writing out an if-then form. If 2 congruent angles are added to two congruent angles, then the sums are congruent. Now I got those big angles congruent. I already did the reflexive property, and I have the little guys from my given. So I am ready to say that these two triangles are congruent. So step 6, triangle JKM is congruent to triangle OMK, and that is angle, side, angle. Now, which angles did I use? In the green triangle, I had angle 2. In the pink triangle, I had angle 4 as my little angle. So I needed step 2. That was an angle 1. I used the reflexive property for KM. That was my side. And then I used the addition property angles there as my last one. So it was steps 2, 4, and 5. And that's how I got my angle, side, angle. All right, now I have those two triangles are congruent. I have, if I put in my picture here, here's segment P, right? Or point P, excuse me. And then over on this one, I have a point P right here. And I already know that those two little guys are congruent. I should be careful how I mark my picture here. I know these little guys are congruent. I'll give this double dash. Okay. And now I could use CPCTC to get the whole big segments are congruent, right? Because just little parts aren't actually parts of my triangle, but I do have this big part and that big part then could be congruent by CPCTC. So I would say step 7 is segment OK, or segment JM, here is congruent to segment OK in those triangles because they're corresponding parts. Corresponding parts of congruent triangles are congruent. So now I have those big segments are congruent. I already knew the top little parts were congruent. So that means I can use the subtraction property to get the bottom part. Step 8, PM is congruent to PK if two congruent segments are subtracted from two congruent segments, then the differences are congruent. So now I know that this part is congruent to this part in my picture. And since I have those two congruent sides, again, remember my goal was to prove that this triangle KPM was isosceles, and I just proved that those two parts were congruent. So my last step, step 9, triangle KPM is isosceles. And now I'm proving it's isosceles. So the if part needs to be if a triangle has two congruent sides, then it is isosceles, right? That's the if-then form that I need. I just found out that it has two congruent sides. That needs to be the if part. Right now I'm proving that it's isosceles. That needs to be the then part. Whew. Not a short proof, so you're seeing, but hopefully you're seeing how everything we've done so far in this chapter just all connects together and builds on itself and lets us do all kinds of really cool stuff with some crazy kinds of pictures. So that's how you use those if-then forms in a proof. So just remember, 3 types of triangles by sides: scalene, isosceles, and equilateral. 4 types of triangles by angles: acute, right, obtuse, and equiangular. And then when proving a triangle is a certain type, make sure you use the if-then form.